Hello, my name is Thomas Trifu, and this is part A of the final project. So the first thing we're going to do is with a new system, we're going to go into geometry with Design Modeler. So now that we're here in Design Modeler, I oriented this so that we're facing the XY plane, and it is visible for us. So now we will click into our sketching, and we're just going to do 3 horizontal lines here at the on the x-axis, and then 4 vertical lines just off to the side. Now we're going to add some dimensions. We'll just use the general tool, 1, 2, 3, and then get some verticals in here as well. And then in the order that we just created them, our dimensions are going to be 1.1176, 1.2192, 1.5748, 1.6256, 0.6096, 0.6096, and 0.889. And then from here, we're going to get some constraints, and we're going to use the midpoint constraint to make this middle block fit in right here. And these will each be given to a respective vertex to be the midpoint. And then from this point, we're going to draw, use the line feature, and then connect the tops to each other. Just like that. And last thing we need to do is go in here and delete all these lines in the center. And we can delete the dimensions as well. They are not necessary anymore. And here we go. Now we've got this wind tunnel looking shape. So next we're going to go to Concept, Surfaces from Sketches, click into the sketch, hit Apply, hit Generate. Here we go. We have an empty wind tunnel. Next thing we need to do, go to Mesh, double click into it. Alright, now that we're here in meshing, we're going to do, first we're going to insert a method. Click onto this face, hit Apply, swap to triangles. And then we're going to insert a sizing, same face, type we're going to keep as element size, and switch the element size to 0.01. From here, we can generate our mesh. Alright, our mesh is done. Next thing we need to do is name the inlet, the outlet, and the walls, which we're going to select all of them using Control, and then name them all together as walls. Alright, now that we've got our name sections and our mesh, we are done here. Alright, now that we're done with our mesh, we can go ahead and update it. And then we can enter setup. I'm going to do 4 solver processes, double precision. Alright, here in setup, we're going to go to models. We're going to swap energy to on. This doesn't really seem to have much effect, but I'll do it just in case. And then here, we're going to switch our model to K epsilon, enhanced wall treatment with pressure gradient effects selected. Hit OK. Now we go to our boundary conditions, inlet. We're going to leave our material properties the same and everything else. We're just going to change our inlet velocity to 5.625. This should give us an average velocity of 15 meters per second in the center, as per mass conservation. Alright, this outlet, we're going to swap this to a prevent reverse flow. And the walls are all no slip by default, but let's just make sure of that. No slip, great. Reference values will be computed from the inlet with the reference zone of the surface body. And here in initialization, let's just initialize. And then we will run calculation with 100 iterations. Alright, our solution is now converged at 8 times 10 to the negative 4 of a continuity residual. Pretty steady decline right here, looks good. Alright, and from here, let's look at some contour maps. So, new, first thing we're going to do is the static pressure. Here's what that looks like. High static pressure at the entrance where velocity is low, then static pressure drops, and then it increases again exactly what we wanted. Dynamic pressure should be the exact opposite. Yeah, exact opposite. Starts out low, then goes higher, then ends lower again. Total pressure should be basically constant along constant streamlines. So it should be constant with a little bit of a bend to it. Let's see it. There you go. It's got some bands on the outside, but pretty much is just constant throughout. Especially this center line, it's pretty much constant. And the last thing is velocity magnitude. This is about the same trend as the dynamic pressure. It starts out low, gets way higher, and then ends low again. All right, so those are our contour maps. Next we can do, first we're going to create some lines. The first line I'm going to do is the horizontal through line. And so this is going to go from coordinates of negative 1.7272, 0, to positive 2.1844, 0. And this is just a line through the center of this longitudinally. All right, and that is now created. We're also going to make a vertical midline, and this is going to have coordinates 0, negative 0.3048, to 0, positive 0.3048. We create that, and now we should have, horizontal through line, vertical midline. Great. From here, we go to plots. We'll do XY plot, new. And first we're going to do along our horizontal through line, and we'll do pressure, static pressure. Very good. Starts out high, drops, and then rises again. Very nice. Then we've got, let's do dynamic pressure. Opposite trend, looks good. And then total pressure. It looks very random and stuff, but that's because if I were to zoom into this a little bit and change this to float, it's hovering around 61.25 to 61.35 the entire time. It's pretty much constant, which is exactly what we'd want for our total pressure. Okay, and then we need velocity magnitude as well. And here's our velocity magnitude chart. Once again, starts out low, then peaks over here, and then comes down. You'll notice with this one, the velocity was supposed to be 15 meters per second in the center. However, it doesn't reach 15 in the center. Why is that? Well, that's because it's not a uniform velocity distribution at the test area. And to show that, we can do, instead of position on the x-axis, we'll do the y-axis and change the plot direction. And the x-axis function, let's make velocity. And we'll swap from the horizontal through line to the vertical midline. And look at that. Here, at the middle of our test section, our velocity spikes up from 0 at each side to make the no-slip condition, reaches a maximum around here, and then it dips down in this parabolic shape as so. What we were measuring before was at x equals 0, or at y equals 0, which is why we got this part right here about 14.5. However, if you were to take the average of these, the integral of these velocities and divide it by the total length that we integrated, you'll see that it gives you about an average velocity of 15 meters per second, which is what we want. All right, let's also, just because, let's graph our static pressure. Wait, no, not static pressure. Dynamic pressure. Same pattern as velocity, except it comes down a bit more here. And our total pressure. Total pressure also follows the same pattern, but notice the change in the axis. This is a different axis. If we swap back real quick to the dynamic pressure, this goes up to about 160, and our total pressure only goes up to about 100, or 95. This is because we have a negative gauge pressure in this area as well, which is dragging down our total pressure. All right, and from there, that's all of the plots and contours that need to be displayed. One last thing that we need to do, which is we need to go here to results, and we need to get our streamlines. All right, here, let's orient our graph, and all we need to do is get some streamlines. So we're going to start them from the inlet. 25 is fine, and you'll see a very simple pattern. Yep, they basically just go straight. They bend a little bit to get in here, and then they diverge a bit out here in the diffuser, but very basic because there's nothing in our wind tunnel. That's for cases B and C, where we actually put something here. But for this case, very basic streamlines. All right, that's it for case 1.